Okay, nice. Welcome everybody to this special seminar in our department. I would like to thank Professor Maiti for being here today and to agree to give this seminar for us. I will introduce Professor Maiti. He's a professor at the Michigan State University. He's has more than 100 papers, and he has been recognized as a fellow of the American Statistical Association, a fellow of the Institute of Mathematical Statistics. He has also been awarded a fellow of the American Association for the Advancement of Science. So he has a very long academic history, and he have supervised more than 40 PhD students, so it's an honor for us to have this he visiting us here. And so the seminar is, the title of the seminar is Big Data, a Perspective from the Statistical Foundation of Data Science. So thank you very much, and that is yours.
Okay, good morning, everybody. You are free to welcome, ask any questions in Portuguese.
Naturally, I'll pass it on to Florencia, right? It will be, my job would be much easier. This is my maiden trip to Brazil through the connection of my Portuguese friends, or Portuguese colleagues. That's the way we came to a policy conference where data science was one of the theme, and I gave one of the plenary talk over there. But as you can see, my heart is much closer to this department. My department is statistics and probability, and this is one of the largest department, I think, in South America, even bigger than us. So I took the opportunity to stop by here, and thanks Florencia for organizing this talk. Hopefully after this talk, some of you guys would be more interested collaborating with us. Like, I'll be happy to recruit some of the students, postdocs, visitors. As a graduate director, I was trying to recruit some of the Brazilian people, but didn't work out that well all the time. I recruited several South American students. Again, didn't work out for many different reasons. Sometimes maybe the language problem. Sometimes we have some like prelim exam. If you like to get our funding, you have to go through our qualifying, and that includes not only the mathematical probability testing as well as your English testing. And one of the things didn't work out well. But hopefully things are changing. World is changing very rapidly. Let's see how much I could cover. But as you can see, that statistics is right now in the crossroad with computer science, machine learning, AI, and it's evolving very fast. So what I'll do, and I have been actually involved actively on my campus, even in Portugal, where we created the data science program in one of the universities over there. I'll take kind of a couple of minutes as my TED talk, but I like to get into pure statistical stuff pretty quickly. What is my view about big data, data science, and how the way statistics is going to play the role for the next decade or so? Okay. Anytime, if you like to stop me, it is not a conference, it is a seminar, so we can talk. We don't need to finish everything, whatever I prepared, like 80 slides or so. Then you have to not only the lunch, then you have to pay for my dinner as well if I have to do this. Okay. So start with the big data. What is a big data? This is again, if I ask all of you what is a big data, I'll get a different answer from different peoples. But what is the agreeable thing is, very quickly we can characterize. So this is kind of taken from what is we accepted in the community, kind of 3 V's. people generally it is innovated by the computer scientist: volume, variety, velocity. So it is just not the size, it's the complexity and the frequency. And I'll give you one example pretty quickly. The example of big data. Just long story short, I take in this way. I told in the other conference as well, I'm pretty good in computing as well, not only the mathematical theory. If I cannot handle these things in my laptop, that means you are dealing with something big data. So it could be size, could be very small, but the computational memory could be so high that you cannot deal with that thing. So I'll come back to this example again. But what is the big data potential, or how the way we deal with, in scientific world, you have to have a philosophy, you have to have a foundations. You cannot just solve everything without the foundation. The basic foundations to deal with big data is that you really, so this is, everybody can identify that this is nothing but a ice cube floating in the water, and generally you get to see the top portion, you don't see anything, what is happening over there. And truly, you are not even interested in here. But what is the problem is that, so you will be interested on the small portion of the big pieces. You really do not like to know the more pieces, but you just don't know which piece would be here, because that would depend on the composition of the whole object, right? Because if it is a hole here, if it is a hole here, all this thing might change which portion would be floating on. So the data science or the statistical principle or machine learning tool would help you to identify which portion we will be able to see, and that's the most important thing we need to know. If you think that you like to know everything, don't come to the statisticians or a scientist, go to some business people and they can solve your problem. That's the way it is, okay? Because the whole mathematical theory stands on these things. All right. So now after the big data, what is the data science to do with the big data? The data science and big data, oftentimes people think synonymously, but essentially it is not. At the beginning, the relationship is like this, like really we cannot handle this big data. Big data needs additional machinery, particularly database management, distributed computing, and it requires new techniques, particularly optimization steps. And the whole optimization theory becomes so much important to handle these big data, and that's the way the electrical engineers, probably you guys know, they're way advanced than the statistics people or even computer scientist people in terms of the optimization. I'm lucky that I got a couple of electrical engineer collaborators who are actually were handling big network data, which I won't be talking today, but this is the optimization thing. So what is the role of the data science and the big data? As we already said, the large portion of big data may not require for a decision making. You really do not like to know. And what is the data sciences helps you to extract the portion what you like to know. And how do you like to do? This kind of two techniques in a broad sense: high dimensional technique, which has been popularized last two decades or so, and some level of sampling techniques in a very non-mathematical sense. Sampling does not mean here that traditional statisticians know here. Mostly it is compression, subsampling, if I get some time. There is a good mathematical theory behind. So these are the two techniques being used to handle the big data. And once you are pretty much equipped with those type of techniques, then these two could be pretty good friend. Otherwise, we would not know, it would be completely black box to us. So where we are essentially going to be in the data scientist stage. And how we'll do it, we'll use the statistical technique to be part of the whole thing. All right. Now, how the way statistics come into the picture. As I said, that my heart is with the statistics. That's what I wanted to be here. Probably this is one of the oldest department, right? How old this department is? 50 years. So you guys should know the history of statistics. If you go back to and I know that you guys have fairly good connection with Britain, like United Kingdoms, because many people are, I think, trained from there. And most of the statistics things originated from there. But if you go back to that, the foundation of statistics, it's with the data. By the way, my early stage of career was in Iowa State, who actually originated number of statistical tools from Iowa State. It came, you know, the Snedeker, even R.A. Fisher was there. It was applied, it was multidisciplinary, it was mathematical, it was computational. And what is the task? Task was much more interpretation, inference, and implication to science and the society. Without application to society, I don't think that the field can grow. So it has been the science of the data or math of the data until the last 100 years or so. But where the statisticians were concentrating, mostly the developing the new statistical tools, because before 50s or so, all the data, how to collect the data, like design of experiments, sampling techniques, all were developed before 60s. Then after that, statistical tools, and you are basically doing this outcome analysis. That's the way our life was, so simple, like the way I graduated, like this way. I did some asymptotic theory, that's it, your dissertation is done. But the life has changed after millennium year, right? So everywhere, the data, basically the definition of the data has changed. Everywhere the data. So I'm the data at this point because you guys are collecting the data already in the online. My watch is collecting the data, my phone is collecting the data, because my wife could see where I am right now. So, sure. But these data, there is a fundamental difference, how the way we used to get the data and how the way we are not now going to get the data. These data are not really ready. These are not spreadsheet. So these are not that authenticated either. You cannot really trust that much as it used to trust, well, this is the sampling data, design of experiment data. This is nothing like that. But nevertheless, you cannot ignore. You cannot ignore this part. Okay. So what happened? Those data are coming through the now new information technologies, through the engineering innovations, information innovations. So as a result, this was like until 2000s. After that, these guys are playing a big role. This includes the computer scientist, information scientist, everybody. But they are the first person who are getting the data first, not unlike statisticians like R.A. Fisher used to get the data first because he was doing the experimentation. But now R.A. Fisher is not doing the experimentations. These guys are doing the experimentation. This is doing, the Google is doing the experimentation. So this part is already here, and this is a large portion of these things. Okay. So DIL is more than science of the data. It is just not the science of the data. This is the engineering part get involved with this modern data science thing. So that makes sense, right? So this is the way evolving. Now let me get back to how the way engineering and one of the example of the big data, that's what I kind of promised. So this is one of the new age data. Some of you can identify already, it is written there. What the image is. Some people are working with our brain. This is the brain, essentially, nothing more. So this is the brain is three-dimensional. So this is the cross-sectional, this, that is the three different type of things. And that's the data. It is MRI, but there could be different technology. Then how do I get the data? I said that Fisher's age is gone. Now this is the engineering technology. This is high-tech technologies. That's the way you scan your data, brain. To get the data, you need to open up the data or the engineering part a little bit. So what is the engineering part? Is essentially what you do, you chop your brain into three-dimensional way into a number of pieces, like 100 pieces here, 100 pieces this side, 100 pieces this side. Okay, that think in this way, but it could be more than 100, in the order of 100. But then what does it mean? And you can think about, we call each of them is a voxels. That could represent one of your neuron. But scientifically, exactly what is happening, I don't know, because it's a machine-driven thing. But what is the most important thing? If I have 100-dimensional here, 100-dimensional here, 100-dimensional here, how many data points you generated immediately? 1 million data points immediately you generated from a single brain. and how much time it takes to take the MRI. If you ever had gone to the machine, like when I started doing this type of work, I take my students to go into the scanner, and some students get out, sneak out, and some students actually take the data, because you need to know what's going on. I didn't want to be a brain scientist, but I wanted to have a feeling about the big data. That's the way I got involved in right now I know quite a bit about the brain, but that's not my expertise. I just wanted to give you some example. So that's the size of the data. I haven't talked about the complexity. So if I talked about the complexity, you might say, oh, this is just the 1 million data point. But really, your brain, you just do not know how the way this neuron work with this neuron next to each other, how the way they work. You just don't know. There are lots of scientific things going on, and which makes it much more complexity. So 3 V's, as you said, that the velocity, volume, and the complexity has to be there. That's the way the big data definition would be. So with the standard thing, this is kind of the size. Now, as you know, there are different technology for your brain imaging. So this is MRI, but if you go with fMRI, then there is a time frequencies. Look at these frequencies. Now then there would be another technology, PET, EEG, all sorts of things. And not only that, a single person can have this all together. So think about how much. So similarly, what we call, this is one piece of big data, this is one piece of big data, this is another piece of big data, but this is multimodal. So different complexity, different science behind these 3 things are there. So question is, now do you see 3 V's here? Anybody here is doing this brain analysis? Like many people I know that interested in network, because brain is the one thing, but oftentimes we don't get involved with so huge data set. When I actually working with my electrical engineers, they even did not have that big access of this data. You have to work with the radiologists, other neuroscientists who has the really meaningful data, all voxels wise. But still, many of the methodology what we have been talking about cannot handle this big data. Still, but there my research is going on. How do we handle this part, which suddenly I cannot talk today. So not only 3 V's, you can see actually from a statistical standpoint, there is a lot more V's are there. Right? So that's the kind of the 3 V's. Any questions so far? That's the 2 minutes TED talk, the big data, data science, and some of our thinking, how the way we are changing our thought process, what we used to think during my graduate time and then when I'm supervising the students. That's the way it is. Now, as I said, what the statistical thinking? So far, we talked about the engineering, most of the data, but there has to be more of the things. As I mentioned, these are the kind of the foundational part. Where the science of the data? What are we doing? Interpretability. Of course, computation is the part of the statistics. If we cannot compute, then nobody is going to take your methodology. Finally, this school particularly, including my school, what is the theoretical guarantee? What is the foundation, mathematical foundation? Empirical validations, that's fairly common in computer science, and we have to do that thing. So this is 2 different way of interpretations. Okay, so what I call these things, not only 3 V's, the big data has 3 S's or 3 plus S's. The statistical complexities are there. I think I'll skip. Okay, I can talk a little bit. So if I go back to these things, then suppose one of the problem could be, now you have the data, then one of the problem could be that you have visited a lab, a MRI has been done, and doctors like to know whether you have certain type of disease or not, right? That's the way this right now, at least in US, AI is going to help a lot. That's what they're installing. I'm not saying that this is the right thing, right way to do it, but that's some of the help we could get. So how do you do that thing? I am putting this thing is nothing but a classification problem. So if I do the classification problem, how do I do this classification problem? Logistic regression, right? you can do the logistic regression. But think about what is the logistic regression would be. That this would be your kind of the feature vector x. What is the dimension of the feature vector? Million. How many brains you could scan? Look at the whole Brazil. You cannot have more than thousands. And what do I mean? That look at the brain data is just not like other experimental data. My brain, your brain, all brain has to be standardized in a certain way. So there is a processing times quite a bit. And at the beginning, one of my students to process like 100 brains, each brain process this thing can take 30 hours even. Okay, so if you are really getting into these things, some of you understand what the complexity involved. It is just not the mathematics. But then, what is the, as I said, that how the way they interact, or in general sense, what we call, they're dependent, right? Like generally people think that the brain is symmetric, this neuron probably talk each other, but we just don't know. But what we believe that there is a dependence, general terms. How the will, I call it general way, spatial dependence, because that's one of the statistics I do. How do I do this? How do I extract this thing? If I do the simple logistic regression, one is the dimensionality problem. Second thing, really you ignore many of the complexity in your analysis. Okay. What is the second thing we could do? So logistic regression is gone. What is the second thing you could do? Why don't you guys, it's a classical school, LDA, linear discriminant analysis, right? That's the meant for. This is the tool that linear discriminant analysis you do, but it's just other way around, right? Your x become like you need to have a Gaussian assumptions, but then what you will do? So I think I do have that. This is kind of the simple thing that basically you have to assume that some kind of covariance matrix about this feature vector. But note that, what is this? This is a million dimensional thing, and you have to invert those things. So it's not a problem free, right? Nevertheless, these are the ways. So starting from Bickel, Levina's work, and then we have done some work, and computers, the electrical engineers have also extended the LDA structure to a high dimensional thing. So there it is there. It is not that this is the kind of the starting point. And one of my students actually explored this thing with some spatial structure, assume that the brain is spatially dependent. That student is now absorbed in Amazon. It's making more than double than what I make. So I asked her to be in as a faculty. She said, well, I'm not going to get half a million in 5 years. All right, forget it. So that you can but the thing is that you have to more equipped. But my conclusion would be, since these things I could spend the time here, but here is basically the cap is that summary is that it is theoretically elegant. All these procedures, what we do, mathematically looks very nice, but it is fairly restrictive. Still, it is not that feasible. If I put that all kinds of multimodal data, fMRI data, it is not really doing that great. And not only that, the generalizability, it's not there. It can work with a very like you can customize some of the cases, but not in all the cases. So that's kind of my learning 2 or 3 years ago. Okay. So where do we go? As I said, these are all nice statistics dissertations, but we need to provide better solutions. If I cannot provide, then the others will come, and that's the computer scientists are already there, who are also dealing with this data. Not only we, actually nowadays the scientists go to the computer scientists first before they come to statisticians. 20 years ago, they used to come first to statisticians. So that's the way. So where will be? Let me, as I said, that these are the other type of thing we do, but what do we should move? I kind of gave you one example of a big data. I talked about some complexity. I gave you some kind of modern solution, like extension of LDA type of things in a high dimensional setting with some dependent structure. but we are still not there yet to compete with other scientists. Now, the deep learning, right? Everybody is talking about deep learning. This is the talk of the, not the town, it's the whole world is talking about the deep learning. Everybody, or ChatGPT you guys are using nowadays, it's really impact the society, not only the science, the society, whole social scientists, everybody is using these things. And the main reason is that, the main key characteristic is that its accuracy empirically scales with the size of the model and amount of the training data. It's a huge amount of data. Very quickly it can crunch these things and give you some outcome. Let's not talk about whether it is valid or not valid, but everybody is using ChatGPT. And this involves, which I will probably open up the deep learning a little bit more, it actually involves billions of parameters involved in that machine, and you need to do the optimization very fast. That's the way it is going on. Okay, so it's just like everybody knows that Aladdin's things, you just ask, oh, I need this thing, they will solve it. So your the deep learning or ChatGPT is just like this. You just give the problem, they will give you the solution. All is well, probably not. Here I'm just trying to say some of these pros and cons, like, okay, it can do many things. You really don't need to assume any specific parametric assumption, blah, 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 all sorts of things. And then I'm also criticizing that different theoretical algorithmic challenges are there, mostly not interpretable, the development mostly algorithmic, all sorts of things I could criticize, but that's the way. You cannot just criticize, you have to keep working on these things. So I will concentrate mostly how the way we are moving along to open up the black box much more in a mathematical way. Okay. So, but what is the key? As I said that 20 years ago, I kind of give up just doing the practicing mathematical asymptotic theory. We have to do the theory such a way we could compute it accuracy, like how the way computer scientists are doing this accuracy, empirical accuracy, scalability, computational scalability, its applicability, its generalizability, foundations. These two are mostly the mathematical scientists, including the probabilist, can get involved, because the theory is lot more involved than what we think. Yes.
The difference between generalizability and scalability, generalizability is to apply in different settings.
In a different settings, like you don't need to create different, like ChatGPT can work in all sets of machine, right? Okay. It's one for brain, one for this. Yes. Like I showed, I gave you one example of the brain. The other example you have seen, I did not talk much. This type of things, like really there could be some growth inside your spinal cord, and how do I know, how do I measure this growth? Really the standard practice, clinical practice does not help us. Can ChatGPT or can my deep learning can help? So that's the type of things. So we are not talking about just one problem, that many problems. As you said, ChatGPT is a good example. You just give everything, they can do it. It's not just the brain, it can do the other things. It can teach on behalf of you, right? Yes.
Words, hard words to say. No, the next one, that one. There is one missing there, which is predictability. Because that's, I mean,
you are right. No, right. Not only one, it can be number of bullets, because that's the way the things develop, right? So that's true. You can put, as I said, that number of bullets are there. It's not done. That's the thing is there. There's a huge opportunities there. It's, whatever, this is the technology. In my opinion, we talk about the discovery, what we today, in 20 years down the line, we'll see the effectiveness, because by that time, many people will experiment from many different perspectives. And that's the way it gets the validity. Otherwise, it doesn't get the validity. Yes. I just skip some advertisements, that number of work with my students, colleagues, you guys can look at if you like to. Let me get into now little bit on the statistical framework of the deep learning. Generally, if you see the IEEE journals, we don't talk about the mathematical part, just they go direct to the algorithms. That's the way it goes. But from a statistical standpoint, as long as we don't see the mathematical model, really we cannot go to the algorithms. So I'll try to open up a little bit more. By structure, this is kind of your input features. It could be high dimensional, whatever it is. Then it propagated through number of layers, oftentimes what you call the hidden layers. And this is kind of the outcome, which could be univariate or it could be multivariate, doesn't matter. The beauty of this thing is that all these things, these are called the nodes. The number of nodes are not necessarily exactly the same. It could be different number of nodes in different layers. But all these input vectors or input are connected to the nodes. Then nodes are connected to another nodes. Nodes are connected to another nodes. You can, and through some nonlinear activated functions. In general, what you can see that if there is some kind of interaction, some dependence, kind of black box is saying everything should be captured because it is not directly propagating, unlike linear regression here to here, it is propagating through the connected way. Okay, so perception is that it's so complicated, it should capture any kind of weirdo dependent structure. What is the connectivity? We just don't know, we don't need to know, but it is taken into account. Okay, that's kind of the general structure. How do I, this is one of the framework which help us to think about, so we need to have a statistic standpoint or probability standpoint and outcome variable and these input variables. So y is our outcome variables and x is the feature vector in a vectorized way. Some of you can recognize this is nothing but called the generalized linear model structure, which takes into account your discrete data, continuous data, pretty large number of data, and I'm just keeping different choice of H1, how the way it takes care of different distributions. So one thing is that this is the how the way this eta 0x is the kind of the machine, how the way it is propagating the feature vectors to your response vector y or response variable y. Okay, and which definitely we do not know. So already I made a comment that this is takes into account all kinds of dependence factor, all sorts of things. The structure, how the way I'm going to talk about that P, that the dimension of this whole thing could be large, maybe even larger than the training sample size, doesn't matter. And we are going to take the approach how to estimate these things, since this is unknown, using the Bayesian approach, and mostly we'll be using the Bayes risk. And there are quite a bit of literature why this is good, all sorts of things. You can, I think the first the Canning Samworth, that's the JRSB paper, who kind of studied all the properties, the optimal properties, etc. So we don't need to go talk to the that master's level statistics things here. What I need little bit of as a or the theoretical progress. So this is the notations for the joint distribution of x and y. That is your actually data. This could be high dimensional, but n data points are there. And what we like to do, these things essentially what is connecting the feature vector to your response. We'll use the deep neural network to approximate these things. Okay, so that's the basically the as soon as you know how the way mean function is connected to a response functions, this should be very clear, except the black box. Okay. So now I'll place this black box as the way I show the diagram a little bit in mathematical structure. So we have to introduce some of the notations. Suppose I have the layer, capital L layers, and Lth layers has the KL number of nodes. So first is K1, K2, KL, none of them has to be same, and Then how the way we can introduce for k L equal to 0, that's the kind of the input part. And the last one, L plus 1, that's kind of the output one. Okay. And this thing goes, one means at this point we are concentrating on one-dimensional output, but it can go to a multi-dimensional output. Then we have to bring a little bit of matrix vectors way that note that the original function at a 0, now we are approximating it through the parameterization theta, and this could be the representations. These are the kind of activation functions, and some whatever the terminology used, these are kind of the intercept terms. V1, V2, VL are the intercept terms, all others are weights, that's what we call. And whole theta, that's the represents the all the parameters that parameterizing the deep net part. Okay. So what is the important thing to think about? The number of parameters, if you have L number of layers and each layer has, or Lth layer has KL, then this is the number of parameters. So look at that. If you have just 100 layers, and each layer has 100 nodes, what is the number of parameters here? You can imagine immediately that. So anybody has an idea how many parameters in ChatGPT? 175 billion, yes, more than that. So you can see how the way it works, right? So in a statistics class, how many parameters did you guys optimize? We have in trouble, right? Even if you use that R code, nowadays I don't use R anymore. So basically what it is highly parameterized statistical model, or highly parameterized non-parametric model. That's the way you can think about from our perspective how the way the deep learning might work. Yes. Yes.
It's the first time that I see a
mathematical representation.
Yeah, and I don't find this easy.
You should look at my papers, then you could get all this. Yes, yes.
Trying to write that on my own.
No. Some people asked me to write some kind of review paper in statistical science, but you know, it requires a lot of time. For me, I think writing review paper oftentimes takes more time, because writing a good review paper takes a lot more time. You have to do quite a bit of experimentation, all sorts of things. But I know that this is in statistics community, it is not so transparent, and that's what I told you in the other conference.
Yeah.
If you like to see the black box more, I'll open the black box here. This is the right community, not the other community. So there, very good point. Okay. So then what would be the case? Everybody now can think about that. I have a statistical model, I have a likelihood function, I have some parameters. Then what we'll do? We have to solve. Now we can get some idea how to solve this thing, right? So I'm coming back now. This is the approximated likelihood, approximated by these million dimensional parameters or billion dimensional parameters. Then this is your true likelihood. This is the approximated likelihood. These two things are there, and what we have to do, we cannot deal with these things from the data. We have to estimate this part. And then once I do these things, I can get one of your PhD students or postdocs, they can do some of the mathematics for me. That's the way it should be, right? But simple thing is that to all these things, some people asked me what are the other assumptions are there. Some of the assumptions would be needed because of the mathematical theories are there. But most important question, whenever I got it, oh, what is the activation function? I do not like to specify a specific activation function because we can work with number of different activation function, but what is mathematically needed, the first order Lipschitz continuous properties has to be there, then the whole theory goes well. Okay. So how to make the inference? Everybody, I shouldn't have showed my thing. Now, since I wrote down this approximated likelihood, how we will solve it? Okay, try anything you try. Maximum likelihood, that would be the starting point, or some cases now the Bayesian things are there. Why Bayesians I'm going? Well, let's not talk about, I don't know. I think this school has number of Bayesian people as well. That's why I'm doing the Bayesian instead of arguing much. So what is the Bayesian would be? In a very simplistic setup, you need some prior distribution for all the parameters. Now your model all parameterized by theta, right? I use just n because of it's a function of the n. So you need a prior, and very simplistic prior you can think about just the Gaussian prior, right? That's the prior thing. And once you have this thing, by the way, the engineers can use left and right much faster than us. But they don't need to know all the properties or anything. So this is we are interested in posterior distribution of the parameters given the data. Simple Bayes theorem applications is there. Okay, and how do we solve it? What is called the Markov chain Monte Carlo. And think about 175 billion or 200 billion parameters you'll be doing with Monte Carlo Markov chain. You have some experience running the Monte Carlo Markov chain, right? Particularly when there is no conjugacy. Here won't be any conjugacy. I don't think that anybody's machine can work. Okay, so that's the way where the computer scientists are way ahead of us. And there are a number of good alternative techniques, including generative adversarial network, variational autoencoders, normalizing flows, you name it, number of things are there, but very algorithmic things are there. Okay. So, but our perspective is that we also acknowledge that MCMC, we love it. The reason is that we understand the theory behind MCMC, but it is obsolete for solving this problem. So we have to go one of these things where most of the things are still black box to us because we really do not understand the mathematical properties yet. What we understood in last 3-4 years, something called the variational base, which is becoming very popular. Again, idea came from actually computer scientists. Very nice idea, neat ideas. As you guys also probably would acknowledge, MCMC idea was not a statistician's idea. The physicist actually brought the idea 1954, 1972. And then we kind of did the theory, like the probabilist got involved, established some theory, it becomes very popular. Some way we contributed, but same way, this is another algorithms are coming back. This is not by the statisticians. The idea is very simple, by the way, what we like. So this is our target. Sorry that there is some discrepancy in notation. Sometimes I use theta, sometimes I use theta n, but you guys are mathematical enough, so can forgive me for that missing typos or whatever it is. So this is our target. And what is the idea is that you really do not like to estimate this one directly. Rather, you use a family of distribution indexed by lambda, and then you optimize this Q star with some objective function. For example, KL divergence, where we know why KL divergence statisticians love it, because this kind of two probability distribution, the closest things, you can do it. And idea is that this is kind of simple diagram. So here we are, but we will be looking for solution in these regions, and they would be in closest in some sense. Okay. But what it is now turns into MCMC was sampling based technique. You were sampling from one conditional distribution, another conditional distribution, another conditional distribution, but now it is flipping to an optimization problem. It is purely optimization problem. And what is optimization problem? Because I like to know that Q for which this should be optimal. So that means I have to solve those lambda. Lambda will be called the variational parameters. But how many variational parameters are there? At least as many thetas are there. Simple, very simplistic stage. So 175 billion. So that turns into the optimization tools, not really. And that's what I kind of said at this beginning. Now we have to really get the help from the electrical engineers who are way, way advanced in optimization than what we do. So
Instead of optimized by theta, you optimize by
lambda, yes. And then you do such a way, it would be close.
Few dimensions, not by
You can have the choice. Very simplistic choice would be you can do like, that's the part of these things are developing. I'll give you one example here. Pretty much for each of the theta, we are putting one of the lambdas. So it is not that less or large, we just don't know which would be the right number, but simple extension would be just like a prior, as many parameters are there, that many prior distributions you need. Same way, as many parameters you have involved here, that many lambdas are needed. That's a simplistic thought, okay? Whether that is the best solution or not, I'm not arguing in this talk. That's a separate topic, but at this point, actually, you'll be optimizing that many parameters. So in any case, we are talking about 200 billion parameters. What does it matter, 150 billion to 200 billions? It doesn't matter, right? So it's kind of your n cross n naught in asymptotic theory. Doesn't matter where you are, n naught plus 1 or n naught plus 2 or n naught plus 3, doesn't matter. Okay, so if you are just computer scientist, you put it there, crunch it, the whole thing, something you might. But since you are the mathematician, you like to do a little bit more, try to see. So basically this part, you do a little bit of math and try to see what is going on and what it would be, what we would be calling that elbow. So that could have these two parts, which could have, you can see a little bit of good interpretation from the statistical standpoint. The first part, it prefers Q to place mass on your maximum likelihood estimate. And the second part encourages Q to be close to the prior. So some interpretation is there. And what we'll be doing will be maximizing elbow by some optimization technique like stochastic gradients, all sorts of things. It could, now you can bring in whatever you have learned from optimization technique. Okay. Now, next 2 minutes, I will skip many things. What I like to show, like 2 years ago or so, I used to leave it right from there. Okay, it's done. But then when we opened up further, because as the way I'm learning more of the more optimization theory, how the way you do the optimization, that can be a game changer, completely game changer. In what sense? I'll take to, so I think I'll skip this part. If anybody likes to know more about the variational base, David Blake Groups has a review paper as well as a theory paper in JASA. So one can look at these things, which gives simple exposition about the variational base. So it is there, but nobody is talking about this high billion parameters or the consistency type of deep net, what we'll be talking about. Nobody is talking about that. So moving to optimization based approach as opposed to the popular sampling based approach. And now number of things, black box variational base, noisy gradient descent. So these are your friend would be Python, PyTorch, TensorFlow, all these things you need to know. Mostly we are now using the TensorFlow for the optimization because those optimization tools developed by the toolbox developed by the computer scientists, which we could use. But as I said, the more mathematical derivations you dip into, it might help you. So what are the few things are there? So if you do the optimization, you know that you have to find the gradient, you have to find the expectation of the gradient, and then how do you learn the gradients, like the learning stage. So these three things are there. As you can see, with this complicated function, none of the gradient you can calculate in an explicit way. Okay, so numerical differentiation you have to do. As a result, you don't have that expectations calculations pretty easily. So you have to do some expectation calculation. So what I'm trying to say, they're involved when you do the expectations, then probably you need to use the sampling based calculation like large sample theory to calculate the expectation. Okay, Now, what your large sample theory said? That the expectation would be much accurate if you have a large sample size. So note that although we are moving away from sampling based technique, but when we are optimizing this thing, still I need some level of sampling to calculate the expectation of the gradient. Okay. So the more sampling I need to calculate more accurate expectations, the algorithm could be much slower. On the other hand, if I take less thing, then algorithm expectation could be inaccurate. Same way, the learning rate of the gradient can have a big influence. Okay. So large story short, number of experimentation we have done, we have developed number of algorithms. What I like to go directly to two different examples. Suppose your response function and x is related, one is relatively simpler, by the way, nothing linear type of things, and this one you can think about, this is lot more complex. These two scenario, and I like to show you that how the way you are developing your algorithms, that can change the performance of your machine. But each cases we are looking in a statistical way, how the, as I said, that what is the statistical part? One is the expectation calculation here, how we are doing that thing, and then the other part is the learning rate. The other things what I wanted to say, that when you are using very small sample to calculate the expectation, what the issue could be? The issue would be variance of the expectation could be very high. As a result, your optimization can take a lot more time to converge. So you could do some kind of traditional like raw Blackwellization type of optimization, or all these things could get involved. And so statisticians actually could help with the optimization as well. So it's kind of a two-way, just not one way. That thing's going on. And so let's take this two scenario, and here is the kind of the outcome analysis. So what I'm trying to, so you can think this is one algorithm, this is another algorithm, and this is the sample size that you need to calculate the expectation. Okay. So that's I am also varying in a number of way. And then how the way you are learning the gradient, sometimes you can have the fixed learning rate, sometimes you can have a variable learning rate. Okay. So 6 different type of algorithms and sample size, and look at the under the fixed, what is the, because at the end of the day everybody like to see the accuracy. So this is kind of the accuracy result, and this is under the fixed learning rate, this is under the variable learning rate. More or less you can see these whole numbers are kind of the same, because you have to match to the accuracy, otherwise nobody is going to buy. If my machine gives 50% accuracy, nobody is going to buy. So it's kind of standardized. But in terms of the time, how is the different? So some algorithm can take only 7 seconds, whereas some algorithm can take 114 seconds. Not just the 7 or 114. Look at the scalability. Now you take it to the billions things. So one machine might take 365 days, and one machine might take only 3 hours. So that's why people will go to Microsoft to buy the machine. Not really they come to Tapsmite to buy my machine, because it takes three years to run. Okay, so that's kind of the scenario one. It gives you some idea that why do you need to think about the algorithm as well. And there are many statistical components inside. Now the scenario 2, even it is much more control. What the scenario 2? Scenario 2 is more complex thing, learning the more complex thing. Look at the time variability. In some cases, the lowest time could be 11 seconds, but the highest time it could be 710 seconds. So not only by the algorithm, by the complexity of the relationship between the feature vector and the response vector, that can also influence how much time it might take, or the scalability, how the way scalability changes. I do not have the proper quantification, mathematical quantification about the scalability, but this gives the research thinking that which one mathematically can I quantify about the computational complexity And that could help us to understand which type of optimization is better in which situation. That's the characterization thing. That's what I was trying to say. But that's there we are for this set of research. I have 1 minute. So this is kind of the empirical things are there. We have, by the way, nowadays you have to do not like a stat paper that you just do one data analysis to publish in a very competitive like Journal of Machine Learning Research or IEEE. You have to do lots of empirical studies. But what else we could do? First thing here, so my students nowadays sometimes scared of me because I won't be happy once they just bring in anything. Probably I'll give them hard time as long as they are not competing with the computer scientist. I would not accept before they get into the theory. So that so little bit of learning. The black box is not a scientifically black box. That's everybody hopefully convinced by now. There are tons of tuning parameters play critical role for this model performance. And optimization is an integral part of modern statistical learning. And I have to give credit to my electrical engineer colleagues where I am being influenced by their optimization part. So what the last thing we could do? In statistics, if you like to publish the paper, then you need some theory. So in a Bayesian thing, one thing at least you do, which we are doing a lot more than that because I also involved in JASA where we promote the statistical theory. But posterior consistency is one of the things you have to do because this is a high dimensional thing. So what we have done, there are two things are there. One is the posterior distribution, of course, but note that we did not work with a true posterior distributions. I worked with a variational approximation. So all these things I have kind of two main theorems going to the assumptions of everything. This one is the posterior consistency related to the true posterior. This gives the what's the rate, how the way the true posterior the posterior distribution concentrates in the Hellinger neighborhood of the true posteriors. And the second thing is talking about, since we did, this is the theoretical piece, really we did not work with that. We worked actually this one, how the way it is, what is the approximation, what is the posterior consistency. So this gives you these two things. And the learning is that between this, then you have to amalgamate these two. So this could be the interesting part for this group of people. For a general deep neural network, the convergence to risk of Bayes estimator occurs at the rate of epsilon 2 power 2-3 for the variational posterior in contrast to epsilon n for the true posterior. So true posterior concentration rate is epsilon n, but the variational posterior is little slower. But from the mathematical standpoint, oh, you guys did not do a good job. But remember that what else we are doing, the computational scalability, no way we could match. So if you would have done the MCMC, probably you could have been here. But go ahead, you can do that part. Okay, so some of the many of the theoretical things, like one of my junior colleague, then this is my students' dissertations. There are a number of other dissertations are coming up. So all this theory, if you guys are interested in, you can look at this thing. So that's kind of the structure. I hope that I opened up the black box quite a bit. What I like to say, so this is the kind of algorithm going behind the ChatGPT. But what is going on here, or what is going on in autonomous car driving? It's not that. It's actually much compressed version because you have to do even much quicker. So there are what the research so as I said that this is related to 175 ChatGPT 3, 4 is 200 billion. But there are a number of situations where you cannot do that part. You have to do it much faster. And how the way we are doing, basically, we are developing low cost, low computational cost. But how the we are doing, idea is that you really don't need to optimize that many parameters. Given the applications, you can actually work with a much less parameters. Like 10% of the parameters. You could do that thing, and still you could compete with that percent of accuracy. I think I do have how the way we are doing basically using that, again, as I said, high dimensional statistics. Another is sampling, but it's a compression. Particularly for the image, compression work well. Yeah, here is a good example that only 80% per city level, that means you use the 20%, 10%, 5%, 3.5% of the parameters, and you can still get some good performance. I think the idea was you can skip some of the nodes, you can skip some of the connections, all sorts of things you could do, and probably, as I said, that we have to redevelop all these things. Things could be a little bit more complicated. Just you have to trust on me, because I need to also finish it here, that we could actually compete what you could have done with the fully connectivity network. We could achieve to the similar level of accuracy with a much less number of parameters. That means it could take fraction of time than what it could have taken if you use the full machine. And that's the way it is. That's the kind of my current research is going on, because and as I said, theory, if you are working as a PhD students, you have to do the theory. And that's why I think sometimes I need to get the help from probabilist as well, because many of the theoretical things, oftentimes I get in trouble. I don't have this answer clearly. But some of the theory I could do. Finally, what is this thing? I think I will skip all this part. I like to give a message. So this is essentially opens up the big data science, not only for the statisticians, also for the machine learners. Because now, as you can see, they are jumping on this type of problem. Computer scientists are not doing fundamental computer science that much. They are much more interested in dealing with this big data, deep net. But as you can see, deep net, actually, we could do all the deep net. But I will never say that just sitting in this lab, I'll do everything. I'll never be able to compete. I need to sit down in a common place. So what I heard, you guys are in a really good situation, because you have the computer scientist, applied math people, and stat people. So ideal place to develop the data science. And I'll stop it here. I think this is good enough for my lunch.
Can you elaborate a little bit more on the Python's lab prior?
Are you a statistician?
What?
Are you a statistician?
Yes.
Yes, I could see that. Yes.
What I'm interested in is how that affects the variational base approximation. Because I mean, now you have not only the space of parameters, but you also have these 2 to the power of whatever Python's lab, structure.
Yeah. So you have to adjust here. The more calculation has to go. So basically, this is the kind of the Python structure. You can see that you could do that for either it will kill some of the weights, or it can kill the whole nodes. But this is the basic structure. But then the algorithm, you have to adjust further. The elbow calculations, there will be some discrete optimization would come in, and that discrete optimization, what we are trying to make it continuous approximation of the discrete optimization, because as you know, discrete optimization is much harder thing to do. So all these things are there. Sorry that I escaped.
Why don't you use that in like horseshoe prior,
That's all these things we have done.
continuous?
Yes, but that doesn't matter whether you do. That's a
Get rid of the discrete,
no. It is. So what you are saying, see, this is the spike and slab. This is your spike part. This is your slab part. Yeah. This slab part is normal. Yeah, but that does not take it away the discreteness. Here you could use, instead of Gaussian, you could use horseshoe, you could use Laplace. That's already we have done. Okay, but that's not the issue. Of course, theoretical issues would be there. The discreteness, because of this G, this is an indicator variable, and this is a dummy variable, that creates the biggest problem. Okay, So
No, but what I'm saying is that if you use spike, the whole thing becomes continuous.
oh, that's the
It avoids
no that you
you're saying like you're combining the spike and slab with the.
I got your point.
I'm not saying that. Just get rid of the spike and slab and model continuously
okay.
with a price that puts a lot of mass around zero and a happy tail.
Yes,
Which is,
yes.
for instance, the horseshoe, but there are a lot other ones. Like
Okay.
the usually prior,
Okay,
the
got it.
normal prior, the triple gamma prior, Fruition Schneider, many other ones. At least in that case, you get rid of these, combinatorial components that you showed in your optimization function.
So that is good.
But spike, what is the difference between a spike and slab? I'm not saying that one thing cannot do the other things, but it's a very automatic way. It can drop the variable. But if you do not use spike and slab, then you have to use some kind of other threshold to drop a variable. Okay, if you do not have spike, then you cannot drop directly, because here essentially G is determining whether I'm dropping a variable or not. But it's open. It's just, we can make many comments. Definitely, that's the different. If you have got 20 PhD students, you can give all this problem one by one. But there is a reason why I personally prefer the spike and slab, because it's directly drop the variables. But if I use just the slab portion, which we have done in many, like horseshoe, spike, all these things are there, but it does not directly drop the variables in this stage. You have to use certain other threshold. And that's kind of the first version of the literature. Some of the computer scientists also have used it. But what I wanted to say, it is there. Okay, it's a good point. It's at least you guys got some idea that what we have been doing. Great. Other questions?
Yeah, I have a bit, but it's not.
So here is one example of this is one of the experiments done by
Computer scientists where they did not use the spike and slab.
My question is a more general one. So we have some results for neural networks, but you showed only the dense architecture.
Mostly I showed the dense part, but the
The
non-dense
results
part.
apply to other architectures as well, like
That's
GM,
what, yes,
they apply.
yes,
Oh,
yes, yes.
that
Yes.
gives some.
That's the kind of the framework I basically presented. But now that framework can be, basically we are extending in all different types.
Okay.
Yes. You got it. I think you. Yes.
So you are using your variational family to approximate the posterior. It's possible to, how do you regularize your, for example, your posterior? Is it possible to regularize the posterior to go from the dense model to the sparse model?
No, you go through, you regularize through your prime distribution.
With the prior distribution. That's the Bayesian, the
Yes,
biggest
so
advantage.
the driver in this case.
Yes,
the driver
yes,
is doing a
yes, yes.
good regularization.
Yes, indeed. Spike and slab is essentially one of the regularized prior distributions. That's what you do, exactly. That's what the Bayesians give a little bit of more advantageous
So
than
in
the
general,
other
the
thing.
models you obtain are sparse.
It's sparse, yes. But you really don't need to sparse if you have really big data. But you can have this. So second part actually the sparse, where you like for the brain applications or the autonomous car driving type of things, then you need to use the sparse network. But when chat GPT type of things, because those guys have really big machine, we cannot even imagine how big machine they have. And they're collecting the data all the time, right? Not only my cell phone, everybody's cell phones are there. So they have the big data as well. See, the mathematically, you need the data as well to optimize all the parameters. So if you have the option, then you can have the fully structured thing. But what I'm trying to say, it is possible to obtain sparse network with comparable accuracy, but I'm not claiming that it can be better than the fully connected network. Okay. Yes.
So you showed the variational base method, and you find the optimization problem is a tough problem. Like to find a suitable member of the class that approximates the true posterior. Do you think that a two-stage method the following propose a suitable and normal, which use part of the data and approximate it with a and find the approximate member in that family that the true posterior, and then you totally shift to using the family. So forget the true posterior. Now I will only compute the posterior using the other data points only within the family. So I'm saying this because conjugation is much easier than facing a complex optimization problem.
Yeah, the issue is that you won't get much of help from the conjugation, even your prior, because you have seen in likelihood
It could be very complicated.
Yeah, but the first one, you find a suitable member, so a lot of computation. So you use part of the data set to do that. You use optimization algorithms, and the second stage you use the conjugation part. So
Can try. There is no yes or no answer because this is the research going on. So you can, and if you open the computer science literature, you will see that every day there is a new algorithms, empirical studies are there. I'm having hard time oftentimes to replicate their whole thing. And also how many things we'll be trying, because as a statistician, what I like to develop in the end of the day, not only the empirical justification, not only the optimization, I have to have some kind of theoretical justification. And once you change all these things, that has got a bit of implication in your theory as well. I have to say that these theories are all still not that straightforward.
Questions? Okay, let's thank again